Welcome to Honors Pre-calculus Flipped Classroom. What we're going to do today is show you our first edition of a flipped video and try to share with you the experience of being a student watching a flipped video. So we're going to flip our classroom. You're going to watch the instruction, and then together we'll be able to practice using the techniques that we've learned. So our first session, we're going to talk about graphing techniques and symmetry. Particularly, there's two types of symmetry today that we'll cover. And the first is line symmetry, and the second is point symmetry. So by the end of class, you should be able to recognize both types, and there are several types of line symmetry. And you'll also be able to recognize and test point symmetry. So why are we learning about symmetry? Well, think about what it's like to graph. If you had to make a table of values and plug in an x value and find out what the y value would be, and you had to create a picture of a complicated equation, it might take you a cumbersome amount of time, or it might be cumbersome for you to plug in a bunch of values and get their outputs. So to find all the solutions for the equation could be cumbersome or tedious. So if you know about symmetry, it can actually speed up your graphing process. So symmetry is going to be a shortcut for you. It's going to allow you to find one point, and if you know that one point, then using symmetry, you automatically will know another point. So it's like you get it for free. The first type of symmetry is line symmetry. So what is line symmetry? A graph of an equation has a line of symmetry provided that the line is the perpendicular bisector of the segments that join corresponding points. Probably hard to digest first time as you read through it. So let me try to explain this definition. And I'm going to explain it using the equation y equals the absolute value of x minus 3 plus 4. So the picture in blue is the graph of y equals the absolute value of x minus 3 plus 4. And a little shortcut to help you remember what absolute value functions actually look like. I remember them as absolute v value. So in blue, it looks like a v, and that's the graph of an absolute value function. So it mentioned in the definition that it's a line of symmetry if it has a perpendicular bisector from point to point. So first, let's look at this point here, which is 1, 6. If I connect 1, 6 over to 5, 6 on the equation for y equals x minus absolute value of x minus 3 plus 4, when I get to the halfway point, this green dashed line, it's actually the segment I created in blue is perpendicular to that green dashed line. And the definition of a perpendicular bisector, if you remember from geometry, is that every point is equidistant to the perpendicular bisector. Okay? So the segment I drew in blue, I added the congruent markings, and you can see the segment here is perpendicular to the green dashed one. And this is true for every point on the function y equals the absolute value of x minus 3. So if I go over to 6, 7, and I connect a segment all the way over to the other point at 0, 7, again, it's congruent on both sides. And this green dashed line is our line of symmetry. Our line of symmetry, you can kind of think of it as a mirror. So from this left-hand side, if you mirror it over this green line here, our line of symmetry, it matches to the other side. Okay. So let me go back up to the definition and try to rephrase what it's telling you. So it says a graph of a line has a line of symmetry provided that the line, and the line we're talking about is the green dashed one, is the perpendicular bisector of the segments that join corresponding points. So the corresponding points were the ones on the graph of y equals the absolute value of x minus 3 plus 4. And the segments, we connected the points, and it made a segment. They were perpendicular to the line of symmetry and equidistant. So the first type of line symmetry that we're going to talk about is symmetry with respect to the line y, with respect to the y-axis. So if you look on your worksheet, it says symmetry can be found by looking at the graph of a function or a relation. We looked at the absolute value of x minus 3 plus 4, and now here I'm going to give you another example. So symmetry with respect to, that particular phrase, you'll hear it over and over. So with respect to the y-axis, think of a graph. Where's the y-axis? It's this vertical axis. So it means that whatever's over here on the left is mirrored over the y-axis on the right. Okay? So that's your line of symmetry, the y-axis. And we can test if an equation has y-axis symmetry algebraically. So here's a little shortcut. The definition says for every point xy on the graph, the point negative xy is also on the graph. So for example, if you had a graph and it had 2, 4 on the picture, then what else would also be on the picture of the graph? It would be negative 2, 4. Okay, so I go back to the picture we started with. The y-axis is over here. Okay, so this does not have symmetry with respect to the y-axis because on the left of it, it doesn't match the right of it. Okay, but the example we can look at is the absolute value of x. If y equals the absolute value of x, if you check out that equation, I'm going to show you what that looks like. You have a couple of options if you wanted to graph y equals the absolute value of x. So you can make a table, you can put it in your calculator, you can use various methods. I'm just going to show you what it looks like. So there's a rough sketch of y equals the absolute value of x. So the y-axis is going to be our line of symmetry. Everything on the left-hand side matches everything on the right-hand side. It's like a mirror image, right? And so if I wanted to test it algebraically, and if you had already made a table, you would see that the point 1, 1 is on the graph. So if 1, 1 is on the graph, what else is on the graph? Our rule said if xy is on the graph, the negative xy is on the graph. So if 1, 1 is on the graph, then negative 1, 1 is on the graph. Now, is that true? So let me go over. I go over negative 1, 1. Yes, that is also on the graph. So the absolute value of x has y-axis symmetry. So in order for you to test this, if you just had the equation and you weren't looking at the picture and you weren't looking at your table of values, what you'll be able to do is to test algebraically is if you plug negative x into the x of the original, and then you simplify it, you have to ask yourself, does it match the original? So for example, if I say, I have my original is y equals the absolute value of x. I'm going to take my original equation, and wherever I saw x, I'm going to put in negative x. Now I have to take this entire equation and simplify it. So if I had y equals the absolute value of negative x, well, that's the same thing as y equals the absolute value of x. So does it match the original? Yes, it does. Since it matches, then it has y-axis symmetry. The next type of symmetry we're going to talk about is x-axis symmetry. X-axis symmetry, as you probably can guess by the name, is that it's mirrored over the x-axis. So whatever's up here is also down here. Okay, so if it's on the top, it's on the bottom. x-axis symmetry has a rule that says for every point xy on the graph, then every graph also contains the points x, negative y. So if xy is on the graph, the point x, negative y is also on the graph. An example equation we could look at is y squared equals x. One way that you could graph this is to make a table of values. And you could say if x was 1, then y would be the square root of 1. If x was 4, then y would be 2. I have that backwards. Okay, let me fix what I just said. So if you wanted to make a table of values, you had y squared. The squared is happening to the y. So not a function we're used to looking at. So you might want to make a table that's yx, and I know I just wrote it backwards, but if y was 1 and I squared the 1, then x would also equal 1. If y was 2 and I squared the 2, it would mean that x is 4. If y was negative 2, then x also would equal 4. So this might become a little bit confusing as you're looking at it. So before we figure out what the graph looks like, let's first test to see if y squared equals x has x-axis symmetry. So in order to test this, we're going to follow the same rules as we did for y-axis symmetry, where you're going to plug in what's changed into the original and figure out if it matches the original equation after you simplify. So what changed? The x stayed an x. The y turns to negative y. So to test it, you're going to plug in negative y into the original equation. Then you're going to simplify. And if you simplify and you get your original back, then it has x-axis symmetry. So let me show you. So my original is y squared equals x. So I'm going to plug in negative y. So I would write negative y squared equals x. What is negative y squared? Since this negative is inside of the parentheses, when I square it, I'm going to get y squared equals x. So here's my original. And once I simplify, I get my original back. So y squared equals x does have x-axis symmetry. Another way to look at how to graph this, and we haven't gotten there yet, and we're going to get there, I promise you, but if I was going to graph it, your graph in the end is going to look sort of like this. Okay. So if you needed to graph it, we have to have y by itself. Our calculator doesn't have a graphing function that you could put in y squared equals x, so let's get y by itself. In order to do that, I would take the square root of both sides. Since I'm the one introducing the square root symbol, I have to consider both the positive and the negative values. So what is the square root of y squared? Well, it's y. And what's the square root of x? It's the positive square root of x, and it's also the negative square root of x, which we usually write as plus or minus the square root of x. Okay. So up here, that's what our graph is going to look like. Third type of line symmetry. This is not in the text, but y equals x symmetry. So where is, first of all, the line y equals x? If I sketch the coordinate plane, the line y equals x means that if x equals 1, if you think about it as a table, if x equals 1, y equals 1. If x equals negative 1, y equals negative 1. If x equals 2, y equals negative 2. Negative 2, negative 2. Okay, so it's going to be this line through the origin, positive slope, or if you think of it that way, y equals 1x plus 0. That's in slope intercept. Y equals mx plus b, that's your slope intercept form. So the line y equals x is this blue line here. The rule for line symmetry with respect to the line y equals x is if xy is on the graph, then yx is on the graph. So to test a point or to show you with numbers, if 3, -8 is on the graph, then what else must be on the graph? You just switch them, -8, 3. Algebraically, how do we test this rule, xy, yx? Let's look at xy equals 24. So in order to do this, I'm going to switch the x and the y. Now, if you remember, the commutative property says you can move things around. So if I have the equation xy equals 24, and to test it, what you do is you swap them. So you swap them in the original, and then you simplify. And once you simplify, did you get the original? If you get the original, then it has symmetry with respect to y equals x. So I'm going to write this as yx equals 24. Is yx equivalent to xy? Well, yes, it is. I already mentioned the commutative property of multiplication allows you to switch the order. Xy equals 24, and yx equals 24 is the same, is equivalent. The last one that we're going to cover is a point of symmetry. So what are points of symmetry? Points of symmetry is phrased by definition as a graph of an equation has a point of symmetry provided that the point is the midpoint of the segments that join corresponding points. So if we think about it in terms of a line and a mirror, then we don't quite have it right. But if you think about it in terms of this example, what you could do is connect corresponding points. So if I connect this point and this point, then my point of symmetry, right here, is the midpoint of the segment that I drew. If I connected this point with its corresponding point up at the top, and I create a segment, again, the point of symmetry creates congruent segments. Another way to look at the origin symmetry, which is the first point symmetry we're going to talk about is origin symmetry. So what's kind of cool about origin symmetry, if you look at the graph of y equals x cubed, I have two pictures of the same graph. So if you look at y equals x cubed, one way to look at a graph and visually know if it has origin symmetry is if you take if you put it on your calculator, you could flip your calculator right upside down. And if the right side up and the upside down version are identical, then it has origin symmetry. Origin symmetry. So if your right side up and your upside down match the graph, you could just tell by looking at it, it has origin symmetry. But we're not only going to be looking at the graphs. We also want to look at the algebraic way to show this. So for every point xy on the graph, if it has point symmetry and origin symmetry, or the origin is at 0, 0 on a graph, so here is the origin, 0, 0. So that's why we're calling it origin symmetry. The origin of the coordinate plane is at 0, 0. So if we have origin symmetry, that is the point we're talking about. So if xy is on the graph, then the point -x, -y is also on the graph. For example, if -2, 8 is on the graph, then 2, -8 is on the graph. So how do you test this algebraically? To test this one, you're going to plug in -x where you saw an x, -y where you saw a y. So you're going to plug in -x for x, and you're going to plug in -y for y, Then you're going to simplify. So kind of cheated. I already showed you what the graph of y equals x cubed looked like. It's this one up here, y equals x cubed. But let's test it algebraically. So if our equation is y equals x cubed, I'm going to do it up here in the corner. Y equals x cubed. That's our original. What I'm going to do is I'm going to plug in negative x where I see an x. Negative x. Keep the cubed. I'm going to plug in negative y where I see a y. Negative y. If we have a third degree exponent, or the exponent is 3, and you're going to cube a negative, it stays negative. So if I have negative x times negative x times negative x, that equals negative x cubed. And it's supposed to equal negative y. So it doesn't really match, but they both have a negative. So the negatives could either cross off, or you could multiply by negative 1 and y. So you want to solve for y. So you're going to multiply or divide, whatever you think about. You want to solve for y. That's our simplifying. Our y equals x cubed. So if you test origin symmetry algebraically, you plug in the negative x, the negative y, and you should get the same thing. So our original was y equals x cubed, and we ended up way down here, y equals x cubed. And graphically, you can see, flip it upside down, has origin symmetry. Okay, last thing I want to talk about is what types of symmetry does the graph of the absolute value of x plus the absolute value of y equal 1 have? In order to do this, you're going to have to test it out, and this is your opportunity to give it a try. Your teacher is going to be available to help you, and we're going to finish this one in class.